All right, welcome. We're going to be doing lesson 1 for applications of derivatives. We have two main goals here that we're going to try to do. We're going to be interpreting the meaning of a derivative in a real-world context, and we're going to be explaining the units of the derivative or second derivative. Feel free to pause for a moment here if you want to read the prompt in this square box. I'm going to be going ahead and moving on to question number 1. So, question number 1. Hot water is dripping through a coffee maker, filling Mr. Michener's mug with coffee. The amount of coffee in the cup in ounces is modeled by this function, where t is in minutes. So we have a situation here where we have a mug of coffee that's being filled up, and the output of this function is measuring how much coffee is in here at a particular time in minutes. So question A is asking us to find b prime of 5. So we need to first find the derivative of this function. So b prime of t. Here we have two separate terms. We have this constant term, so the derivative of that is going to be 0. And then we have this term here, which is our exponential function. So it's going to be negative 16 e to the negative 0.4 t, and then multiplied by the derivative of that exponent there, so times negative 0.4. There's a little bit of cleaning up we could do with this. We can multiply these constants together, but I'm going to go ahead and leave it like it is. Okay, so next step is to evaluate this derivative that we've just figured out at 5. So b prime of 5. So again, that's just going to be achieved by replacing our t here with the value 5. And I'll go ahead and show that on Desmos. And as you can see here, we've got a value of 0.86614, yeah, long decimal there. I'm going to go ahead and round it to 3 decimal places for this example. All right, so that is 0.866. Okay, so that is the value of b prime of 5. That is our output of our derivative function at 5. Part B, what are the units of b prime of 5 and how do you know? I'm going to start with this kind of how do we know what the units are. So remember that the derivative is a function that gives us the slope of our original function, or the rate of change of our original function at any given value, right? So slope is the change in our output, change in y, divided by the change in our input, change in x. So we look at our original function here, b of t, and the output of that function is the ounces of coffee that's in a cup. And our input, t, is our time in minutes. So for this situation, our units, our output units are ounces, and our input units is minutes. So if the derivative is giving us the slope of our original function, it's giving us ounces per minute. So here we have a value of 0.866 ounces per minute. Another way of thinking about this, or another way of kind of figuring this out, is remember that b prime of t, another way that we sometimes write derivatives is db dt. Right, so dB, the change in B, the change in our output here, B, which is the amount of coffee in the cup, per or divided by dt, the change in time, which is in minutes, so ounces per minute. Okay, we'll go ahead and scroll down here a little bit to look at question C. So question C asks us to explain the meaning of b prime of 5 in the context of this problem. I'm going to kind of follow a bit of a formulaic process when I'm doing this. And we'll do it in blue. Why not? So at t equals 5 minutes, the amount of coffee in the cup is increasing. It's increasing because we have a positive rate of change, positive 0.866, at a rate of 0.866 ounces per minute. I'll go ahead and move that up so we can see the whole thing there. So at t equals 5 minutes, the amount of coffee in the cup is increasing at a rate of 0.866 ounces per minute. And so that gives us the context of this problem and what this value that we calculated before really means. It's the instantaneous rate of change that's happening exactly at 5 minutes. At 4 minutes, it's probably going to be changing at a different rate than this versus at 6 minutes or other times. Yeah. All right, we'll go ahead and move on to question number 2. Question number 2. Mr. Michener is roasting marshmallows over a fire. The table below gives selected values of the temperature, T of x, in degrees Celsius, of the metal stick x centimeters from the heated end. I think this one is helpful to have a picture to sort of illustrate what's going on here. So we have our fire, and we have a stick that's standing there, and somewhere on there we're kind of roasting a marshmallow, right? And that distance, however far from the end, that's our x, our independent variable. And what we're measuring is the temperature that is happening at that particular distance from the end of the stick. So for instance, at 0 centimeters from the end of the stick, so all the way at the end there, the temperature is 100 degrees. 1 centimeter, right? So just a little bit in, it's 93 degrees, and then at 5 centimeters, it's 70, and we're moving farther away, and the temperature is going down and down and down. Anyway, estimate T prime of 4. Okay, so in this situation, we're estimating the value of a derivative given the table of our function. We don't know what's actually happening at 4 degrees or even, particularly close to it. I mean, 1 and 5 are somewhat close, but 4 is somewhere in here. And again, we don't know what the temperature is there. What we can do instead to estimate or to approximate is we can use these values here around 4, right? These are the closest values to 4 that we have between 1 and 5 and between these temperatures. And so we're going to calculate the average rate of change between these values and use that as an estimation for our rate of change there. So T prime of 4 is equal to the change in our output variable. So apologize, that's the wrong value to use first. 70 minus 93 divided by 5 minus 4. Right? We're just kind of doing y2 minus y1 over x2 minus x1, right? Kind of our basic slope formula there. So anyway, a little bit of simplification, that equals negative 23 over 4. And if we divide that and get a decimal value, you can say this is around negative 5.75. And so that is our approximation. I should use some approximately equal to symbol there, right? This is approximately the value of our derivative at 4. What does this mean? What does this value t prime 4 mean in the context of this problem? So let's go ahead and talk about the unit part here. Remember, the derivative is the change in our output divided by the change in the input of our original function. So this value is degrees Celsius, because that is our output unit, per or divided by our input unit, centimeters. So this is saying that the temperature is changing at this rate in degrees Celsius per centimeter that we move from the end of the stick. Okay, let's go ahead and kind of write that out a little bit more formally, kind of like we did on the last problem. So at 4 centimeters from the end of the stick, the temperature is decreasing this time at a rate of 5.75 degrees Celsius per centimeter. So in this situation, we have our context for our input variable. It's at 4 centimeters. That's what that 4 represents. From the end of the stick, the temperature is decreasing. Again, we know it's decreasing because we have a negative rate of change. It's decreasing at a rate of 5.75 degrees Celsius per centimeter. Again, that's kind of contextualizing everything about that value, right? Because this is the particular rate of change that we're estimating at this value, 4 centimeters. All right, let's go ahead and move down here and look at our last question. At Cedar Point, Mr. Michener notices all the people coming and going. The rate at which the people enter the amusement park is modeled by this function, E of t. The rate at which people leave the same amusement park on the same day is modeled by L of t. this function. Both E of t and L of t are measured in people per hour, and time t is measured in hours after midnight. Okay, so we have a lot going on here. We have two functions, E of t, which gives us the rate at which people are entering amusement park at a particular time, people per hour. And then we have another function, L of t, which is similar, but it's people leaving the park at that same time, t time. And then t, time, is measured in hours after midnight. So t equals 0 to represent midnight, t1, 1 a.m., t2, 2 a.m., and so forth. We're going to create a new function, h of t. So let h of t equal E of t minus L of t. So we're talking about the people entering the park, the rate at which people enter the park, minus the rate at which people are leaving the park. By subtracting them this way, right, entering minus leaving, we're sort of getting a net change. If this value is positive, that means that there's going to be more people entering than there are leaving, which means that the, overall population of the park would also be increasing, would have a positive rate of change. If this value is negative, E of t minus L of t, means L of t is greater and we have more people leaving, which means that the amount of people in the park is decreasing, so we get that negative rate of change. Anyway, we're going to calculate h of 17. So again, that would be equal to E of 17. So how many people, what's the rate at which people are entering the park at hour 17, minus L of t, the rate at which people are entering the park at this particular time as well. Okay, so let's go ahead and go back to Desmos. I already calculated these values and I just want to show them here. So if you take a look, we have the second row here, we have 15,600 divided by this value, right? And so we get our value for E of 17, which is 380.4875. I'm going to go ahead and round that to one decimal place. So we'll call it 380.5. And then here we have our leaving function, again, evaluated at 17, and it comes out to be 760.76. Again, I'll round that to one decimal place, and we'll call that 760.8. And let's go ahead and get those off the screen. And we'll go back here. So this is 380.5. That's the rate at which people were entering the park, minus 760.8. That was the rate at which people were leaving the park. I'm not sure if I said that correctly. This is entering. This is leaving. So you can see we have more people leaving the park, so we're going to get a negative value, and the overall population of the park is going to be decreasing. And so when we calculate this, we get a value of 380.3, negative 380.3. And again, that's going to be measured in people per hour, because both of these are also measured in that people per hour. Okay, interpret h of 17 in the context of this problem. Right? I've already sort of done this, but let's kind of formalize this a little bit more. So at t equals 17, which corresponds to 5 p.m., if we kind of figure that out, the amount of people, let's not talk about that, not the amount of people, the rate at which the amount of people in the park is decreasing at a rate of 380.3 people per hour. Okay, so let's go ahead and kind of go back over that and just make sure this makes sense. So at t equals 17, which corresponds to 5 p.m., so at 5 p.m., the amount of people in the park is decreasing, again, because we have a negative rate of change here. This is a rate, people per hour, is decreasing at a rate of 380.3 people per hour. Cool. Now, this is a little different than the last one because we didn't calculate any derivatives. We didn't calculate any, even approximate any derivatives, because both E of t and L of t kind of already were derivatives in a sense, because they were giving us a rate, right? It says the rate at which people leave the park and the rate at which people enter the park and people per hour, right? So since they were already outputting a rate, in a sense, they were already kind of giving us the value of a derivative. Anyway, let's go to move forward and answer this last question, C. What would the units of E prime of t be? So let's go ahead and go through a similar idea. So E prime of t, this is our entering function, or the derivative of our entering function. E prime of t is going to be the change in E of t divided by the change in t, right? And E of t was measured in people per hour. People per hour. And t, obviously, again, is measured in hour. So by looking at that, we have people per hour per hour. Or you may remember this from like physics or something. This sort of resembles acceleration. It's kind of like the rate at which the rate is changing. It's how is the kind of the acceleration of the rate of change for our people entering or leaving the park. So another way of thinking about this would be people per hour squared. Again, kind of like acceleration, like meters per second squared. Anyway, we'll go ahead and move on finally to our last part where we kind of summarize some of these ideas. So I already got some stuff underlined, but that's okay. So a derivative is related to the original function by giving us the instantaneous rate of change slope. Rate of change is slope, right? At any desired x or input value. So a derivative gives us the rate of change of our original function, right? Units, the units of our derivative of f prime of x is always going to be the units of f of x, units of our output of our original function, per the units of our input variable of our original function, right? So when we are looking at, the amount of coffee in ounces per minute, right? And then the units of f prime, which is the second derivative or the derivative of the derivative, that's going to be the units of the output of our derivative divided by the units of, again, our input variable. Notice how the denominator there, that remains the same. It's kind of what we're looking at on the top. So this is sort of similar to that last example here where our E of t function was kind of already a derivative, and so it was giving us people per hour per hour. Okay, lastly, this is sort of a framework that we can use for interpreting a derivative in context. So at x equals some particular value, make sure to include the units. The blank, right? What are we talking about? The output context. What is our function measuring? Is it measuring coffee? Is it measuring people in the park? Is it measuring the temperature of the, on the stick that we were looking at? Is increasing or decreasing, right? If we have a positive rate of change, it's increasing. If we have a negative rate of change, it's decreasing. And what is the rate? Make sure to include those units, right? So this is just kind of a structure that we can use to interpret what the meaning of a particular derivative value is. Anyway, hopefully that was helpful. Try those check your understanding problems, and I'll see you guys next time.